Remember, at the beginning, we introduced this notation H0, which is a list of algebra, which is a real list of algebra of G consisting of all the real diagonal matrices. And I also mentioned its relation with this H without zero. However, some of you might have already noticed that we have never used this notation again. Now we are going to use this. This notion will be used to define a positivity on the set of roots. First, we notice that for real diagonal matrix, namely H with entries H1 through Hn that lives in H0. So this means this is a real diagonal matrix. Clearly we have, for any root, EI minus EJ in delta, we have E sub I minus E sub j applied to H is Hi minus Hj. This is in R, a real number, because this matrix is a real matrix. Given this information, our next step is to introduce the notion of positivity within H0 star, which is still spanned by E sub I minus E sub j's. So, in order to define this positivity, there must be some basic axioms. So let me ask you a question. What is your memory of positivity in high school or elementary school? When you first learned the notion of positive numbers, what property of them are expected? For example, we would expect that for any real number that is non-zero, either the number itself is positive or its negation is positive. On the other hand, you would expect that if you have two numbers, A, B in R, that are both positive, then A plus B would better be positive. And A times B should also be positive. So now, analogously, what axioms do you think we should have in order to define the notion of positivity on H0 star? Analogously, we would expect the positivity defined on H0 star to have the following properties. First, for any phi that is a non-zero element of H0 star, exactly one of phi and negative phi is positive. And secondly, the sum of positive elements is positive. And any positive multiple of a positive element is also positive. So those two axioms are the ones that we would expect that the definition of positivity to have on H0 star. So 1 and 2 are basically the expected properties for the positivity of anything. Whenever you see the notion of positivity in mathematics, you should somehow expect the properties like 1 and 2 should hold in some way. However, those two properties cannot be used for a criteria to tell if any specific element in H0 star is positive or not. They only gave what properties that positive elements in H0 star should have. So we have to think a little bit harder about how to define the positivity on H0 star. So now the question is how to tell a specific element in H0 star is positive or not. The resolution to this question is not actually unique. Here, we're just going to introduce one approach. The idea is the following. Recall that H0 star is spanned by the elements ei minus ej's for I not equal to j over R. And remember, we had the notation for this set. This is called the set of roots, denoted by delta. So for simplicity, you can also write this as the R span of delta. And in particular, this H0 star is containing R span of E sub i's, where I is from 1 through n. This is not equal because, remember, H0 has the dimension n minus 1 because the matrices in here all have trace equal to 0, and that one relation offsets its dimension by 1. So as a dual space of a finite dimensional vector space, H0 star also has dimension n minus 1. So the dimension of this is strictly less than the dimension of this. And as a result, this containment is a proper containment. One attempt is the following. For any element phi in H0 star, phi can be expressed as the linear combination of E sub i's. Maybe you want to use the positivity of the coefficients to define the positivity of phi somehow. However, the bad thing is, because this space is strictly containing the R span of E sub i's, this expression is actually not unique. And because it is not unique, if you use the positivity of coefficients to define the positivity of phi, there will be an issue of well-definedness. And we have to get rid of the trouble that you may have multiple expressions for phi. Because this may also be equal to another linear combination. of E sub i's. However, if we add one more restriction to the coefficients in this expression, we'll be able to make this expression unique. Indeed, we have the following claim. Every element phi in H0 star can be uniquely expressed as phi equal to the summation from I to 1 to n of A sub i's times E sub i's with the additional assumption that the summation of A sub i's is equal to 0. Here A sub i's are in R. And this unique expression will allow us to define the positivity of H0 star. And now let's check this claim. First, let us verify the expressibility. For any linear combination, C sub j times E sub j's sum from j equal to 1 to n in H0 star notice that the sum E1 plus E2 plus En is equal to 0 as an element in H0 star. Why is this true? To verify that this guy is a 0 element as a linear functional on H0, it suffices to apply this to any matrix in H0. So assume this matrix is from H0. This means all the entries are real and the sum of H1 through Hn is equal to 0. This means this is a diagonal matrix with the diagonal entries all real and their sum is equal to 0. And by the definition of E1 through En, this is equal to H1 plus H2 plus Hn, which is 0. And because this is arbitrarily chosen from H0, we have E1 plus En is equal to 0. Now, we can rewrite this sum as follows. This sum is equal to the sum from j equal to 1 to n of Cj times Ej minus. Now, we're going to transform this sum into another sum where the coefficients have the sum equal to 0. And the trick here is to subtract the average. So we're going to subtract 1 over n times the summation C1 plus C2 plus Cn. And this thing must be 0. That is where we are going to take advantage of E1 plus En. And this can be rewritten as the summation from j equal to 1 to n of Cj minus this average times E sub j. And now the coefficients of those guys will have sum 0. Because if you look at the sum, this is precisely C1 plus dot Cn minus C1 plus dot Cn. Because for this part, when you take the sum, you get n times 1 over n times C1 through Cn. And this will give us 0. So this verifies the expressibility. Now let us prove the uniqueness. It suffices to show that if you have the sum of Cj times Ej's equal to 0 with the sum of coefficients equal to 0, then C1 equal to C2 equal to all the way to Cn is equal to 0. This is because if you have two equal expressions, you can always reduce them by taking the subtraction into just one expression with the same restriction. So it suffices to consider this case. Okay, now how to prove this? The trick is to apply this to many elements in H0. Hopefully, if we keep trying, we'll make every coefficient vanish. So now let us apply the sum to, say, E11 minus EII, which is in H0, for any I greater or equal to 2, less than or equal to n. So what do you get with this application? There are two terms in this sum of n things that may not be vanished. They are C1 times E1 applied to this, which is 1. And Ci times Ei applied to this guy, which gives us C sub I times 1. So this is C1 minus Ci. This, together with our assumption, will give us the following system of equations. C1 minus C2, C1 minus C3, all the way to C1 minus Cn are all equal to 0. And don't forget, we have the assumption that the summation of C sub j's is equal to 0. And if you take the sum of all of them, this will give you there are how many? There are n equations. N times C1 the rest will cancel out. So this gives you n times C1 equal to 0. And because the field of complex numbers have characteristic 0, so this will give you C1 equal to 0. And follows that C2 through Cn will all equal to 0. And this verifies the uniqueness, and therefore the whole claim.